So we finished in our last discussion talking about the scientific method, talked about the steps. The first step, can someone tell me again what the first step is of the scientific method? Yeah, identify a problem. So you just kind of observe the environment, observe whatever environment you're interested in, whether it's a marsh, a hospital floor, or a group of animals in their natural environment. You just sit and observe. And then you come up with a question. You formulate a question. And then from that question, you make a statement. And what is that statement called? Say it louder. A hypothesis. And a hypothesis is a what? What type of statement is it? It's an educated guess, so it's based on observation, right? But it's a statement. What does it end with? Question mark or period? A period. So what type of a statement is it? A prediction. Very good. It's a prediction. That's a key word that you should associate. When you hear the word hypothesis, think of prediction. So if you were given a list of statements, you'd have to pick which one is the best hypothesis. What are some things we talked about when we were talking about grades and attendance in our little sample hypothesis? What do you have to think of when you're formulating a hypothesis? It's an if-then statement. It could be written that way. It makes it a little easier. But what do you have to know about that statement? If you're going to make an experiment from it, what does that prediction statement have to include? A measurement, something that's measurable, right? You can't say students who come to class do better. Do better at what? How do you measure do better, right? Like when I ask a patient, how are you feeling? Oh, I feel like crap. Well, that's not a choice in our drop-down menu. Can you be more specific and give me a number of your pain, for example, or are you nauseous or whatever? So the hypothesis has to have information that's measurable. So it's important that we understand this because when you do your lab report, you're going to do 2 of them this semester, make sure when you write your hypothesis, it's including information that is measurable. And we talked about variables last time. Your hypothesis should contain what 2 types of variables that all the scientific experiments have? What are the 2 different variables? Yeah, independent, independent. Can someone tell me some characteristics of the independent variable? How do I identify that? Yes, far back corner. Okay, we always put it on the x-axis. And how can we identify the independent variable when we're reading a scientific experiment? How do we know what the independent variable is? Yes? Yeah, it's what you're changing in the experiment. So if I'm talking about a different experiment, let's say protein shakes and weightlifters. People who lift weights and drink protein shakes will build more muscle mass. Okay, will gain more strength, whichever you want to choose. Let's say muscle mass. So we're going to measure the circumference of their arm over time. So the independent variable is what I'm going to change what I'm going to change in the experiment. I can't change their muscles in the experiment, right? But I can change whether they get a protein shake or not, right? So that's the independent variable. It's what I'm going to change, what I'm going to vary in the experiment. And then how can we describe the dependent variable? What are some characteristics in identifying that? Yeah, what you're physically measuring. So it has to be measurable, right? We have to have a measurable variable. So it might be height or, like I said, the circumference of a person's arm if they're weightlifters. And where do we plot that on a bar graph or on a graph? On the y-axis, so the vertical axis, that's where your dependent variable goes, right? And then we look for relationships. Okay, what are other variables in an experiment? So there's the independent variable, dependent variable, and what do we call that set of variables that we don't want to influence our experiment, want to keep it the same? Control variables. So control variables are the 3rd type of variable that we want to make sure are the same. So if we're talking about weightlifters and protein shakes, what would be some control variables in that example? Yes? Yeah, the amount of protein powder and what else? Okay, the amount of weight, because obviously if some people are lifting more weight, they're going to build more muscle mass just based on that. So they have to have the same weight that they're lifting. What else? Yeah, the pattern of weightlifting for sure. Frequency, number of reps. What else? The same exact type of lifting, yep. How about the individuals we bring into the sample? Yep, what do we call that group of people? Yeah, the control group. So they're not exposed to the independent variable, right? Another thing that we will want to make sure is our subjects are the same, right? Wouldn't that make a big deal? Like, could I put a 45-year-old and a bunch of 18-year-old males in the same weight room and group together? Would that be fair? Definitely not, because we know that our ability to build muscle mass goes down with age. So you want to keep the sample size similar, all those variables. So we have to really think about those variables. And again, there's so much information coming at us in social media and in the newspaper and on the news. I mean, the news, no matter what side of the political aisle you're on, is so biased on both sides. So it's hard to really get good quality news, because I listen to both just because I like to hear what both sides are saying. And even when I lean to one more side, they say things that are totally incorrect. And I'm like, oh my gosh. But that's the nature of the human brain. We like to observe and come up with our perception sometimes of what we see. And that's really, if you think about politics, it's all about what is your perception of the way things should be run. Some perceive it this way and this is 100% truth. Another person perceives it this way and it's 100% truth. That's why science becomes so important, because you can have these perceptions, these educated predictions of what you think, right? Like if we have free health care, everybody will be healthy and our economy will boom. Other people say, if we have free health care, only the wealthy will be paying for it and premiums will go up, healthcare competition will crash, and economy will collapse, right? So there's two different total perceptions of what they think will happen. Well, the only way to really know is to do it, right? Is to conduct an experiment. That's a pretty big experiment when we have the entire nation, right? And it could be a devastating experiment if it doesn't work, or it could be amazing if it does. So nobody's willing to take the risk. So we're lucky with science, we can take small populations and take these risks, right? The vaccine debate is another thing that's out there. A lot of people are saying don't vaccinate. But if we look at the data supports vaccination. But if you look in small groups, the data might say, hey, I have a child, got the vaccine, they became autistic right after that. So it must be that. Again, you have to look at data. So you are young people, you're going to be seeing a lot of information. There's a lot of stuff out there. There's a lot of conspiracies out there. Always think of the scientific method, and you can look for abstracts on this stuff. Like another example are vitamins and supplements, right? There's a lot of stuff out there saying that if you take this, you'll be, it's awesome. You take this spice and you add it to your tea and it's going to do these wonderful things. Do some research on it. See if there's actual research on that product, because sometimes there is, and it really supports it. I do the same with myself. I look into things and I say, is this supported by research? And it is. So there's a lot of good research out there. We just have to make sure we're accessing it. And the key thing when we're accessing it is knowing what's quality and what isn't. So that's our next topic then. Primary versus secondary sources of information. When we talk about primary literature, we're talking about literature that's been published and reviewed by professionals in the area of quality research, and they have said, yes, this is a quality research experiment, and we support it. So when we look at primary literature, you're looking at journals, right? Like the AMA, American Medical Association. That's what doctors, belong to, and they submit research based on their patient population, and it's peer reviewed, and they come up with conclusions, and they say, give them a stamp of approval that yes, this is quality research, and we know that this is now true. So these are things when you're writing papers in college, this is where you need to get your information. As educated people with college degrees, we rely on primary literature. Secondary literature is written by people that might be giving an opinion, they might be giving their personal experience with a product, and that's great. I mean, we have a lot of infomercials, right, of people that are big and bulky and strong on the different types of exercise equipment, right, showing how awesome it is, but is it really any better than any other type of exercise equipment? Because people can be in a jail cell and doing plyometrics in their jail cell using nothing but their own body weight and be big and buff and muscular. So it doesn't necessarily mean that equipment is so awesome, right? So it's subject to interpretation. So anything that you look for online that ends in a .com is typically an example of secondary literature. So .com, and you should write that down so you remember this when you go back and do your lab reports. It's not peer reviewed. These are things that anybody can put out there. Anybody can create a website by paying the host of that website to put it out there, and you can put anything you want. And that's why if you come up with some crazy idea, some crazy product that is amazing, you'll find people out there that will support you because it's out there. Anything's on the internet nowadays. So it's can be very popular, but it's not technical. When we say objective, what does objective mean? Objective data. Here's an example. You come in for a doctor appointment, and I get your weight, I get your height, I get your blood pressure, I have you sit down, and I ask you how you're feeling. And you say, I'm having pain in my right leg because I twisted my ankle yesterday. Which of that data that I gathered is objective? Yeah, height, weight, and blood pressure are objective because you can't argue it, right? If I measure someone and the ruler says this, it's that, right? Blood pressure, if the blood pressure cuff says this, that's what it is. I can't make it up and say, well, maybe it's not that. I mean, there's always some error in machines, but whatever is indisputable is objective data. Like if someone vomits, they vomited. That's objective data. If they say they're nauseous, is that objective data? Can I verify nausea? I can tell you right now I'm nauseous. Could you verify that? No. That's subjective data. So subjective data is here. So subject to an author's interpretation, subjective data. Like I could say I brought my baby in, she was perfectly fine, gave her the MMR vaccine, a month later she was diagnosed as autistic, and we could see her decline. That's subjective data, right? Because no one else could verify that. So objective data is measurable, directly observable. Subjective data is what a patient says when you ask them. The biggest thing we do in nursing is ask people about their pain. And a person can be laying there, reading the paper, and I'll come in and I'll say, what's your pain? Oh, it's at a 10. I need some heavy-duty pain medicine by IV. And then you're like, oh, okay. Well, you're relaxing, you're reading the paper. A pain of 10, that's people that are like gripping the handrails of the bed and crying. And I've had, when women are in labor, they're like that. That's a pain of 10. That's what I picture a pain of 10. But again, it's subjective. For that person, they may think 10 is just annoying pain. So we have to be careful when we're looking at data that it's not subjective. And one thing in education, there's a lot of subjective data because can we truly measure learning? Like if you get an A on the test next week, does that mean you learned that material, and if I talk to you 5 years from now, you'll be able to tell me all about the information on that test? You're shaking your head, Xander. Why?
Because it just means you had the information learned from the test.
And how do you define learning? How do we define learning? Is it memorizing and putting on a test and it's gone when you walk out the door? Have you had classes like that? Where you're reciting it as you come in, and then the test comes, oh good, and you write it down, and now I don't have to think about that anymore, right? And then what happens? Gone, right? Or when you meet somebody and they tell you their name, and you're, oh hi, so-and-so, and then you walk away and you come back an hour later, you don't remember their name anymore? So what is learning? It's hard to measure that, so it's very subjective. Okay, so primary literature, so things like journals, anything that ends with a .gov or a .edu are more likely to be primary literature. So .gov, .edu, put that under this column, That's primary example. So when you're looking on the web, look for those types of endings. And then if it's .com, then anybody can put that out there. And I was in a computer class here at Western. I won't tell you the website, but it was some governmental website. And she accidentally said, okay, let's look at some government. We were doing a computer class, it was like 25 years ago. And she's like, okay, let's put in this governmental website, and I'll just make it up, capitolbuilding.com. She meant to say capitolbuilding.gov, but she put capitolbuilding.com, and we all put it in, and we got this website of naked women in like flag pasties and bikinis, and it was a lot of elderly people. I was there with my mom, trying to learn computers, and I'm like, oh my gosh, so people will put stuff out there to shock you. Yes? What? .org would be another, that kind of depends, because there's organizations that are very subjective, yeah, because there can be like the anti-vaccine organization, so that's a little questionable. You'd have to kind of sort through that. I could say that could go under either, honestly. If you're looking up a disease, going to the .org website for that disease is a great website because it's put out by professionals, like the Multiple Sclerosis Association is a .org organization. It's great. So it just really depends on the topic that you're looking. If it's a controversial topic, the .org may not necessarily be good literature, but if it's a disease, yes. What was I saying before that now? Oh, there's another website. My son, oh my goodness, my son and I, he was like 11 at the time. He wanted to look up who's the big basketball guy that always shoots from the outside that people say he's not a player because all he does is shoot from the outside. Kobe, is it Kobe Bryant? Stephen Curry, yes. So we were looking up Stephen Curry's shooting form, something like that. We just searched it. We got the most disgusting sexual, like oral sex, nasty stuff flashing on the screen and really obnoxious. And I was like, oh my gosh, because my 11-year-old was like, what is that? But they do that. These pornographic websites they put this stuff under innocent search terms. So crazy. Anyway, so primary versus secondary, make sure when you're doing your lab reports that you're using primary literature. And if you're searching something, you're looking at primary literature. Because some of you, unfortunately, are going to have some unfortunate medical diagnoses. And they're going to say, we want to give you this treatment. And you're going to be like, is that a good treatment? Is that going to impair my fertility? Or maybe a significant other family member, same kind of thing. You can be the one to say, hey, let's research this before we make this decision. Let's not just go with the doctor's word on this. Because sometimes doctors aren't aware of the latest and greatest treatments or the side effects of treatments. Or maybe they're not going to tell you the side effects of treatments until it's too late. So you need to know how to search primary literature. Okay, so next topic then, moving on, is the chemistry of life. So we're going to do a quick review of chemistry because that was a prereq for this class, so we're not going to spend a lot of time on it. But chemistry is the study of matter. Like I said, what is biology the study of? The study of life, yeah. So living things, living matter. This is matter that is not living. So we're talking about solids, liquids, and gases. So anything that takes up space and has a mass, we call that matter. So again, solids, liquids, and gases. Those are made up of elements. Elements are in the periodic table. They're the most simple substance that cannot be broken down to other substances. And a compound is a combination of elements. So what are some examples of elements? Iron is an element. We need iron in our diet to make red blood cells. If you're not getting enough iron, you might be anemic. If you find yourself tired, short of breath, and pale, it's very common for college-age women. A lot of guys, everybody in here is college-age. I think we don't have any non-traditionals this semester. Anemia is a big problem in your age group. So if you are someone who gets sick a lot, you feel tired all the time, even when you get enough sleep, and you're pale, short of breath when you're just doing basic exercising or walking across a parking lot, you might need a little iron supplement. And you can get that checked at the doctor pretty easily. So iron, oxygen, carbon, sodium, anything you see in the periodic table of the elements, right, is an element. So when we combine elements, again, we call that a compound. So what's an example of a compound? Two or more elements combined together. Water is what? H2O. Another thing that we define a compound is how it's bonded together. So a compound is usually a metal and a nonmetal. So it's on one side of the periodic table with the other side of the periodic table. And they, one gains, one loses electrons. We're going to talk about that. So water is actually a special thing that we call a molecule because it shares electrons. It's kind of a special, but a compound, what's this popular compound you put on your food? Sodium chloride. That's a popular compound. It's ionically bonded. The sodium is the metal, the chloride is the nonmetal. You bring them together, you've got salt. If you pull them apart, sodium is a silvery, soft, solid metal that you can like scrape it like almost like a putty. It's really soft. And if I put a chunk of sodium in water, it'll explode. So it's very reactive with water. Now I put salt in water all the time, right? In all of our foods we have. But if I combine sodium with chloride and it loses that electron, it changes its properties completely. And then it becomes this solid white substance, right? So chlorine by itself is a toxic green poisonous gas. But again, if it gains an electron from sodium and forms that ionic bond, totally changes its properties and it's table salt. So a compound has characteristics that are different from its elements. And that's the classic example is sodium chloride. Sodium is an explosive reactive metal with water. Chlorine gas is poisonous. Put them together, table salt, totally different properties. So different than the elements' properties. So 25 of the 92 elements we see in the periodic table are essential to life, but these 4 are the ones that make up most of matter: carbon, hydrogen, oxygen, and nitrogen. Carbon is the framework, it's the skeleton of most compounds that make up living things. When you talk about organic molecules, they contain carbon. So that's the key element that we see in living things is carbon. So everything else are some of these extra, you've heard of these ions before, calcium, potassium, we need those in our diet. And trace elements are just small things that are needed. We're not going to talk much about those. But these are the things that make up most of living things. Again, carbon, hydrogen, oxygen, and nitrogen. So CHNO, chno, if that helps. So when we look at the elements, they're arranged in the periodic table by the number of electrons and protons they have. So when we review atomic structure, if I look at hydrogen, for example, the gray represents the nucleus. What subatomic particles do we find in the nucleus of cells? Do you remember? Yeah. So in the nucleus, we have hydrogen has an atomic number of 1 in the periodic table. So that tells us we have 1 positively charged proton in the nucleus. And then it's balanced by the subatomic particles that are found outside spinning around the nucleus, which those are called what? Electrons. And we'll just give them a little E negative symbol. So that little yellow dot there outside of the nucleus of hydrogen is the 1 electron. And we know there's 1 proton, and electrons are negatively charged, protons are positively charged, so therefore atoms represented in the periodic table are considered neutral because they have a balance of positive and negative subatomic particles. So if I look at hydrogen then, it has 1 electron in its outer energy level. We call that outer energy level a valence shell. But there can be more energy levels, because if I look at some of these other ones, there's 3 outer energy levels. So if I look at these, and I look at all these here, let's look in this row, how many electrons do you see in that first energy level of all these different atoms? How many electrons can they hold? There's only 2, right? So the first valence shell around the nucleus can only hold 2 electrons. Then that valence shell is full. Then we have to go to the second one. And how many can the second hold? 8. And after that, every one after that, 8. Okay? So when we look at valence electrons, they're in the outermost shell. I want you to write this down. The first shell can hold a max of 2 electrons. The second through whatever shells can hold a max of 8 electrons. That's the octet rule. The octet rule says that there can be 8 in the outer energy level. So if they have a full shell, they are stable and non-reactive. So if that energy level is full, they are stable and non-reactive. So if I go back to this, which atoms shown here have full outer energy levels and are inert or non-reactive? There's 3. The noble gases, and where do we find the noble gases? On the far right of the periodic table. So if I look at helium here, it is full. That first outer energy level can hold a max of 2. It has 2. There's no other electrons, so this is stable. It is unwilling to share or give electrons to any other atom. So helium does not react with other things. So when you inhale helium from your balloon to change your voices and everybody laughs, right? Is that going to interact with anything in your body? Nope. No. So if I pop a helium balloon and release that gas into the air, no big deal, right? Helium does not react. Neon, again, does not react. It's full. Argon, all examples, there's 8 in the outer energy level, and that's all there is. So how many, so just looking at this structure alone, how many electrons does neon have? 10. Its atomic number is 10. It has 2 in the first energy level, 8 in the second energy level. It has 10 total electrons. So how many protons does it have? Everything in the periodic table is balanced. What? 10. Okay? So the atomic number tells us about the number of protons and the number of electrons. So if it's atomic number 10, it's in position 10 on the periodic table. It has 10 protons, 10 electrons. Okay, so if they have incomplete valence shells, they want to share via bonds, a covalent bond, or transfer via ionic bonds to get their valence shells full, so they're stable. Say what? Oh. Do you have the note? You don't have the notes in front of you? So they're going to share to make a covalent bond or transfer to make an ionic bond. So that's the key thing we're going to distinguish now. Is it covalent or is it ionic bond that's involved for getting these outer energy levels to be full? So a covalent bond is where we share a pair of electrons. So for example, if I look at, let's look at, what's a good example? Oh, I haven't. That's not, yeah, okay, nonpolar covalent, good. So nonpolar means equal. Polar means we're pulling one direction a little more than the other. So if it's 100% equal, we say nonpolar covalent. So here's 2 hydrogen atoms. When they're in the environment together, hydrogen atoms will find each other because there's an attraction because of those outer energy levels not being full. They are attracted to each other. They hover over one another So the valence shells are kind of migrating among the two energy levels of the two different atoms. So it feels like to this hydrogen atom that there's 2 electrons there. And for this hydrogen atom, it feels like there's 2 because they hover close to one another and those electrons are in each other's outer energy level. So they're sharing those electrons. Covalent. So just think of cooperate, cohabitate, right? It's 2 people sharing some activity. Collaborate. It's all about co-transport. Yes? No. No, because there's 2 separate atoms. They still have the nucleus with the 1 proton. Yep, yep. So then we write that as H2. This is hydrogen gas. H2. And we used to use, I believe, this is the gas we used in the Hindenburg, which was like a big blimp that we had over in, was it Germany? I think so. And it exploded and blew up and people died and it was terrible. Yes? Yes, yeah, very good. And we find covalent bonds when we see nonmetals bonding with other nonmetals. Hydrogen is kind of an exception. It acts as a metal and a nonmetal. So it's one of those odd little atoms. But everything else is pretty straightforward. If you look in the periodic table of the elements, it's in the back inside cover of your textbook. But to keep everything online, I'll just pull it up off the web. Of course. Let's see, let's go this way. Trying to look for a nice color-coded one. Okay, well, if I go to the far right side, let's do it this way. If I go to the far side, you start with boron, silicon, arsenic. That's where we start to get from metal to nonmetal. So the yellow and the red and the green, the red, the green, the yellow, these are all metals. And then we get into the transition metals, and then we get to row 14, column 14, we're into the nonmetals. So the green and the blue are truly nonmetals. So hydrogen is one of those oddballs. If you notice, see how it's colored blue, and but it's over here? Because we have to arrange the periodic table by the number of electrons and protons. So that's why it's over here on the left, because it's in column number 1. But then when we look here, it actually fits in with these nonmetals. So chlorine gas would be Cl2. What type of bond would be between chlorine gas? Ionic or covalent? If we said covalent is between 2 nonmetals, ionic is between a metal and a nonmetal. So chlorine gas, Cl2, what type of bond? Covalent, because it's chlorine is the blue, right? It's on the far right side of the periodic table. It's a nonmetal, so it's going to form covalent bonds. How about CO2, carbon dioxide? What type of bond? Covalent. Carbon's on the right side of the periodic table in the green, and so is oxygen. Covalent. So when you look at a lot of our compounds, organic compounds, sugars, fats, proteins, they are mostly carbon, hydrogen, oxygen, and nitrogen. That's the atoms that make up proteins, for example. What type of bonds? All covalent bonds. But if I look at, how about potassium chloride? Ionic, because potassium's on the left side and chlorine's on the right. So that's between a metal and a nonmetal. Yes? Exactly. Between 2 metals, or 2 nonmetals, sorry. Okay, so let's go back. Equal sharing. So what you could write under this nonpolar covalent is 2 nonmetals Another example, fats are nonpolar covalent. So anything that is a lipid or a fat is made up of carbon, hydrogen, and oxygen. All those atoms are bonded together and equally sharing those electrons, and therefore it is a nonpolar covalent bond. And because it's nonpolar, it doesn't mix with polar substances where we have unequal sharing. So let's talk about that. Yeah, what we've talked about so far, equal sharing, are all nonpolar covalent bonds. Equal sharing of electrons, which means that this hydrogen is sharing this electron equally. These electrons are not being pulled toward either of these nucleus any more than the other. They're smack in between, and they're equally sharing. Okay, so it's like playing a tug of war, where like if you put a little flag in the middle of the rope, it's not moving. They're equally pulling that electron, and its electron is staying put, equal distance between both nuclei. Okay, polar covalent means someone's a little selfish in this relationship, which is like most relationships, right? Someone takes a little more sometimes than the other does, right? So we can see how many electrons are in the outer energy level of oxygen. It has an atomic number of 8. So how many electrons are in the outer energy level? The valence shell. Not 8. Remember, the first one can hold 2, so what's left over to go in the second one? 6, yeah. So there's 6 outer energy levels, or sorry, 6 valence shells in the outer energy level. And how many does hydrogen have? 1. So therefore, when elemental oxygen comes near hydrogen in the environment, how many does hydrogen need to fill that outer energy level if there's 6? How many does it need? It needs 2. So hydrogen has how many in its outer energy level naturally? 1. So in order to keep hydrogen happy and oxygen happy, oxygen's going to need 2 hydrogen atoms, right? To pull near its nucleus and steal one from the one hydrogen atom. Not steal it, share it. And share another one with another hydrogen atom. So that's why we have H2O. Oxygen needs 1 electron from one hydrogen, another electron from the other, and they're sharing. But oxygen is a little more selfish. So it's saying, I want that electron a little closer to me, thank you very much. And as a result of that, what is the charge on electrons? Negative. So how many protons does oxygen have normally? Okay, it has 8, but if it pulls 2 more in a little closer, it's going to be a little more leaning to 10, right? Which makes it a little more negative, because if I bring in extra negativity, how do I feel? You even think of emotions. If you're near someone who's giving you some negativity, how does it make you feel? A little more negative, right? So we can see in this diagram that oxygen has this little symbol here, making it slightly more negative because these electrons from hydrogen are being pulled a little closer to it. And the hydrogen atoms are kind of losing a little bit of that negativity because of the selfishness of oxygen. So therefore, they're a little more positive because they're losing some of that negative from that one electron that's going a little more toward oxygen. So because of this, oxygen is a charged, not oxygen, water, a water molecule. This is H2O. It's a slightly charged molecule because of this unequal sharing. So we call it polar covalent. Polar means polar. It means there's 2 different ends, right? Like the North and South Pole. They're separate from each other. So they're a little less balanced. This one's a little more negative, the oxygen. The hydrogens are a little more positive. So therefore, what happens then if another water molecule comes near this? Let's look. Try to find it good. Here we go. Positive and negative are attracted to each other. Let's look at this one. Look at this one. So this is a water molecule. Here's the oxygen. Here's the two hydrogens. Notice that the hydrogen of a nearby water molecule is attracted to the oxygen of another molecule. And why is that? Oxygen is slightly electronegative, or electropositive, we said, right? And the oxygens are slightly electronegative. So they're attracted to each other. And what that does is it creates a skin on the surface of water, which we call surface tension. And water kind of sticks to itself, doesn't it? What happens if you dip your finger in water and bring it out again? What does it form on the tip of your finger? A droplet, because water sticks to itself because of this electronegativity, because of this polar covalent bond. It does. Yeah, and we call that adhesion because your skin, too, is a different surface, and that is attracted to the charged particles here of the water molecule, of the electropositive hydrogen, electronegative oxygen. So let's take a 5-minute break, and I'm going to show you a little video of how surface tension works between water molecules. So we'll come back at 51. Okay, so these black arrows represent hydrogen bonds. Those are weak bonds, but strong enough to create a skin to prevent things from falling through the surface. And here's another example. These water striders, you've seen those in ponds, right, in the summertime, that they just kind of skim across the surface. Perfect example of surface tension, that they're lighter, and with those long legs, they can distribute their weight, and the strength of those hydrogen bonds among those water molecules is higher than the downward force of that water strider. So in this little video here, we can see how the same thing occurs with putting a paper clip on the surface of the water, and it doesn't sink because, again, the strength of those hydrogen bonds forming a skin on the surface of the water is higher than the downward force of that paper clip. And water sticks to itself, which we call cohesion. So going back to our notes, water sticking to itself, these are some terms you should know, and I'll have this as part of our vocabulary review, but cohesion are water molecules sticking to themselves, okay, by hydrogen bonds, right? And adhesion is when water sticks to other surfaces. For example, in the summertime, you set your glass down and it's sweating, it's condensing water on the outside of the glass, right? Because it's hot outside and you have a cold drink. It kind of sticks to a glass table. Have you noticed when you pick it up, it kind of sticks? Or bartenders can slide a drink down the bar. If it's a little wet on the bottom, it just glides along, right? That's adhesion because it's between two different molecules. And this is really important because this is how water works its way up from the roots to the leaves, is by adhesion. The water in the soil is attracted to other water molecules inside the root. So that's what type of attraction? Water to water? Cohesion, and then it sticks up the sides of the vessels that carry the water to the leaves by adhesion. Okay? Water sticks to other surfaces, adhesion. So if it's water to water, we call it cohesion. If it's water to something else, we call that adhesion. And it's all because of this unequal sharing. The hydrogens are slightly positive, the oxygens are slightly negative. So make sure you highlight that, you know which is which one is negative, which one is positive. And again, the hydrogen of one molecule is going to be attracted to the oxygen of another because opposites attract. If this is slightly positive, it's going to be attracted to the slightly negative oxygen atom. So that brings us to the other type of bonds, and that's ionic bonds. Ionic bonds happen between a metal and a nonmetal. So make sure you write that down on this slide. Ionic bonds are between a metal and a nonmetal. The metal usually has an extra electron in its outer energy level that it wants to give up, so the next one below it is full with 8. So if I look at sodium, where does sodium fall in the periodic table? What atomic number does sodium have? If I just count up the electrons here, I can actually figure it out. Looking at this diagram for sodium, how many electrons does it have in nature before it combines with sodium or with chlorine? 11. Yeah, 11. So it has 2 in the first energy level, which is full, right? There's only 2 here. It has 8 in the second energy level, and it has 1 in the third. It's not stable with only 1. So if it gives up that electron, just completely ditches it and gives it to chlorine, that third energy level goes away, and the second energy level is full with 8, right? Would everybody agree with that? Well, chlorine has a different situation. Its atomic number is what? You got 2 in the first, 8 in the second, 7 in the third, so that's 17, right? So it needs 1 more electron in that third energy level to get to 8. So if sodium gives up its electron completely to chlorine, both are happy, both are stable, and they form an ionic bond between these 2 atoms. So this is what it looks like now. Sodium only has 2 energy levels because it lost the electron to chlorine. But if I think of the protons that we started out with, sodium has an atomic number of 11, so it has 11 protons in its nucleus. How many electrons does it have now? 10. So if I have 11 positive charges and 10 negative charges, what's the charge on the sodium? I have 11 positives and 10 negatives. I have a plus charge left over, right? So I say that sodium is now called an ion. It lost an electron. I write that as Na plus. Na plus. And chlorine, we said, had 17. Now it has 18 electrons, and the protons didn't change, so it has 17 protons because that's just based on the atomic number. So now it has an extra electron. It is 18 negative, 17 positive. So what charge does chlorine have? A negative. So chlorine is considered an ion. Now any atom that has completely lost or gained electrons, we change their name, we call them ions now. And if it's a positively charged ion, we call it a cation. It looks like cation, right? It's not cation, it's called a cation. And if it gained an electron, we call it an anion. So lost electron, cation, has the T, lost, T, cation. Gain electron has the N, it's an anion, and it has a negative charge. So gain, anion, negative charge. Think of all the N's there, right? So that's an ionic bond. These are the strongest bonds we see, okay, in compounds and molecules that occur in nature. The weakest bonds are hydrogen bonds, and that's good because we can easily break apart water, right, and go swimming in it and do everything we want to do in it. Use it for mixing other things. It's great for that. It's a solvent. It dissolves things, right? Other polar covalent things like sugar, ionic compounds like salt, we can dissolve that in water because those are all charged things, right? But if it's uncharged, if it's nonpolar, water does not mix with nonpolar things like oils and fats and waxes. Those are all nonpolar substances, and those don't mix with water because they're not charged and there's no attraction there to dissolve. And we'll look at this here. So this is what sodium chloride looks like when it's bonded together to form a salt. It's made up of these ions that are ionically bonded, right? Sodium, chloride, they can separate from each other. If I put this in water, it will dissolve, and those sodium ions are charged, right? Because they lost an electron. So the positive sodium is attracted to what of the water molecule? The oxygen. Remember, the oxygen was slightly negative because of that unequal sharing. So the water molecules surround the sodium with the oxygen facing that positive charge. And the chlorine atoms, what parts are attracted to the negative chlorine of the water molecule? The hydrogens. So they surround these ions and actually separate them. But if I get rid of the water molecules, so now I've got salt water, this will dissolve and become salt water, and it looks like this. But if I take all the water molecules out, what do I end up with again? With that, right? In the wintertime, do you ever be embarrassed, look in the mirror, and there's like dried salt underneath your nose from when your nose was running and then it dried and then left the salt there because we have salt in our mucus? Same thing with tears. You sometimes will see, like if you're outside doing outdoor sports or just working outside, you'll start to see a little, then you come in, you see dried salt right in the corner of your eyes as that evaporated. So normally it's dissolved and looks like this. So ionic, anything that is charged can dissolve in a charged water molecule solution, right? But if it's uncharged, it can't dissolve. Okay, so like we said, hydrogen bonds are the weakest bonds, and they form between water molecules. And that allows that little water strider to zip along on the surface. So water is polar. We already talked about that. So what are some other features of water? Spending a lot of time on water, right? Pretty boring, right? But it's not, because water is hugely important to our environment. Our environment is mostly water. So we need to really protect our waterways because that's most of the Earth's surface, and we know that we're losing, with rising sea levels, we're losing water, and that affects the environment. So we got to really be smart about water and protecting it. And it's interesting, the number one thing I can say right now, what I'd like everybody to think about is when you go to Quick Trip and you buy two things. Let's say you go to Quick Trip and you buy a burger and a bag of chips. What do? And a soda. What do? You're going to eat that right away. You're hungry. Oh, I'm going to get some chips, soda, and a burger. I'm going to eat that. So what do? Check it out, put it in a plastic bag, right, and hand it to you. And what do you do the second you get in the car? Take it out of the plastic bag, and what do you do with the plastic bag? Throw it away. A lot of people do, right? How long did you use that plastic bag for? 5 minutes, maybe? Where's that plastic bag going to be now? It's not going to be used again, unless you do reuse it. That's good for you if you do. But how many people open up their drawer and they have 100 plastic bags in there, right? If you go to Target, I believe, you can recycle those plastic bags. And they'll break that down and reuse that. What the danger of plastic bags, let's say you put it in the garbage, or let's say you put it in your car, and you just throw it on the ground, right, like my kids do and I do myself sometimes. And then all of a sudden you open the door and the wind blows and sucks that bag out, and it's a really windy, snowy, crappy day. Are you going to go chase that bag across the parking lot? Probably not, right, if it's nasty out. So that bag blows and blows and blows, and I'll post a video for us to watch in lab. That bag will blow across the surface. It'll end up in a stream. That's the only thing that's going to stop the blowing, unless it gets caught on a tree or something. But eventually what happens is those bags make it to a waterway, and then they travel down that stream to a lake, and then the lake goes to a river, and then the river heads down to the ocean. And these bags, we have a miles and miles around island of plastics in the ocean. And if you're not aware of that, you'll be aware of that by the end of the semester. And that's where a lot of these bags end up, is floating, blowing across the surface and ending up in waterways. So the best thing you can do today to make an impact on your environment, which has little to no effort, is when they say, do you want a bag? Say, no, that's okay. And scoop it up in your arm and take it to your car and eat it. You don't need a bag for 2 to 3 items, right? Or if you have some people with you and you're buying 4 to 5 items, say, hey, you grab that, I'll grab those, let's go. We don't need all these plastic bags. Yes? Yeah. Right, if you're organized enough, bring a cloth bag, that's the best thing. For big shops, yes, that's perfect. Or put it in your backpack. It is. Keurig's great idea. Oh, I love Keurig's. Those little cups, where do they go? They stay around in the environment for a really long time. The medical environment is terrible. Every time you pull off gloves going into a room, in the garbage. But does that mean we should contaminate all of our patients and not wear gloves? Definitely not. That's something that we need to work on. And if someone wants to go into chemical engineering, plastics engineering, great field, because if you can invent a way to recycle, and we do recycle a lot of our plastics, but not nearly enough. The medical environment goes through huge amounts of plastics. Every time we give an injection, it's a plastic barrel on that, injection on that syringe, and it goes in the garbage. Okay, so back to this. Water, it has this cohesive behavior. It sticks to itself. So maybe write that down again to remind yourself when you're studying what does cohesive behavior means. Sticks to itself. I might give you some examples, saying a water strider goes across the surface of a pond. Which property of water does that describe? That's cohesive behavior. It has an ability to moderate temperature. You know that if you live near a major lake or waterway, is it warmer or colder? Depends. It depends on the environment, right? So sometimes it's cooler if you live like up in the Midwest and that water takes a long time to cool down, like up in Duluth, right? Where the temperatures are normally a little cooler and the lakes are cooler, that makes it colder. But if you live, say, in the lakes, larger lakes where the temperature is warmer, the temperature can be a little warmer in the wintertime. Like in Milwaukee, the temperature is warmer if you live near the lake than it is further from the lake. And they get more moisture, they get more snow near the lake. In Milwaukee, we call it lake effect snow. So it impacts the environment around it, yes? It doesn't really stick though, because it moves across the surface, because the surface of insects is usually this waxy, kind of sugary covering called chitin. It has a little bit of stickiness, but the reason why it doesn't push through like us is because of the cohesion is stronger than the weight of the, but there's a little stickiness. You're right, there is a little stickiness of the bug to the surface. Adhesion would be how water can work its way up like a glass tube, like a capillary tube, because but it's a mixture of both actually, because it's it's cohesion that pulls it up, but it's adhesion that makes it stick to the glass tube. Or if you put your finger in a drop of water and it comes out and you have a drop on the end of your finger, that's adhesion as the water sticks to your finger, but it's cohesion that the water sticks to itself. So they coexist, right? Adhesion and cohesion, yeah. Okay, so it can moderate temperature. The water in your body is mostly water. So when you go outside and it's 10 below, you don't freeze solid because you're all water, and that water takes a lot of energy. It has to lose a lot of energy to freeze, and it takes a lot of energy to heat up. So if you heat up something in the microwave, here's a perfect example, something that has a lot of sauce to it, like a pizza, right? So you put pizza in the oven and has a lot of sauce to it, and you take a bite of it, you will burn your lips, right? Because it has that water in the sauce that takes a lot of time to cool down. Where if you heat something else up, like a hot dog in the microwave, and you take a bite of that a little bit later, there's not as much water in the hot dog, and that cools down a lot faster. So people can be in a t-shirt and shorts and be ice fishing in the spring, can't they? Because it takes a long time for the ice to melt, even though the air temperature is warm. And the same thing, it can be cool outside and the water can still be not frozen because it takes a while for water to freeze. It really absorbs temperature differences well. It takes a lot of energy to heat up and a lot of energy lost to cool down. Yes? Hypothermia is when your core temperature goes down. Yeah. Yeah, because our blood has plasma, which it's about half plasma, which is mostly water. Yeah, so as the tissues start to cool, your extremities start to cool because there's less water and blood in our extremities. Yeah, then your vessels constrict, and all the blood is converted to your core to keep your core organs alive. And then as temperature drops more, yeah, that the blood cools. Well, the tissues cool, the blood tries to warm it up, can't, and then that cools and people die. And then when we cool the environment down in the body, enzymes don't work well and people get really tired and sleepy. So you've watched movies, right, where people are trapped in the snow and ice, and they always say, don't fall asleep, right? Don't go to sleep, don't go to sleep. Because if you go to sleep, you're gonna stop moving, and then hypothermia sets in and people die. So freezing to death is actually not the worst way to die, because you get really tired and then you fall asleep and then that's it. And when people pass out in the snow from drinking, like I said, their blood vessels are dilated from the alcohol, they lose heat from their blood faster that way. Yeah, good question. Okay, water expands upon freezing. So as it expands, what happens? It gets larger, right? And if we increase the volume, it becomes less dense. So where is the ice in our lakes? Top or bottom? On the top, on the top. And as it expands, there's air in that expansion that allows for a little insulating layer. So it's important, it's good for our lakes to expand and form an ice sheet on the top, because that helps insulate the water below and keeps the organisms that are living in that water alive. If we have really, really cold temperatures and our lakes freeze all the way down to the bottom, that's going to kill everything in that lake. So having that insulating layer allows for those organisms that bury themselves in the bottom of the ponds, like the frogs and the turtles. Where do they go in the wintertime? They're buried down in the bottom of the pond underneath that insulating layer of ice. And we can walk around on the surface of the ice in most cases, but you got to be smart, right, and make sure that's safe. And its versatility as a solvent. So it dissolves, so this is the key thing you should write down here so you remember, it dissolves polar, covalent, and other ionic substances. Polar, covalent, and other ionic substances. It does not dissolve nonpolar things. It does not dissolve fat, oils, waxes. That's why we use that as barriers. Our skin has a waxy outer layer so we don't soak up water and become a balloon coming out of the bathtub. Ionic, yep, yep. So sugars and proteins have a little bit, protein, a little bit of ability to dissolve, but sugars are all covalently bonded and dissolve. So we already talked about, this is a polar covalent bond within a water molecule, but among water molecules, the dashed lines are the hydrogen bonds, right? And that's what contributes to surface tension. So like I talked about, we look at water flowing through the roots, going up the tree and out the leaves. Cohesion pulls the water as it's lost through the leaves. It pulls that water molecule up, and then it's able to go up these conducting elements, which we'll talk about when we get to the plant unit, by adhering to the sides of that, and that's adhesion. So when we look at the specific heat, which means it takes a lot of energy to heat up water and it takes a lot of energy to cool it, energy loss to cool it down, it's because of these hydrogen bonds. When we break hydrogen bonds, heat is absorbed, and when we form hydrogen bonds, heat is released. So this is what allows temperature changes and the seasons to occur, and everything doesn't die because of this high specific heat. Animals go under the water where there's a lot of moisture and that insulating layer of ice. And we know too, have you heard people, maybe your parents or yourselves, if you ever worked with landscaping, that when we have snow cover on our bushes around and flowers around our homes, that actually insulates and protects them. When we have really cold winters with no snowfall, that can destroy our perennials and plants and bushes around our house. Have you heard of winter burn? that can happen? Yeah, because that insulating layer of that expanding snow provides a little lower or a little higher heat in those really cold temperatures and protects them. So that's why if I'm talking about boiling water versus water vapor, which has more temperature, which has a higher temperature? When hydrogen bonds break, so I have liquid water that has hydrogen bonds together. So I've got these water molecules, right, that have hydrogen bonds. And that's what a liquid is when those atoms are bonded together and they're sliding past each other. But when they break free from the surface, what does water become? I have liquid water, and I keep absorbing energy, breaking bonds. What happens? Those water molecules separate and become a gas. So a steam burn is much more damaging than a boiling water burn because of the energy that's absorbed when we're breaking bonds, when we're heating up water and turning it into a gas. That absorbs, the energy is absorbed by that liquid, breaks the hydrogen bonds, releases them to the air as a vapor. So when you open up, say, like a commercial dishwasher too soon and that steam comes out and burns someone's arm, that can be very dangerous. So we have to be very careful with steam when we're around water vapor. Boiling water will burn you too, obviously, right? But it's much more serious, a steam burn versus a liquid water burn. All right, so we already talked about this. The density, water expands. That keeps it on the surface. If it sank, that would be a problem because everything would die down in those lakes and ponds. So moving on to chemical equations then. Any questions about water? Lots of information there. All right, so chemical equations, whatever goes into an equation, like if we're taking sodium and chloride, sodium plus chloride are the reactants. They're going to react. The products after the chemical reaction occurs would be sodium chloride. If we're taking water and oxygen, so these are both gases in the environment, when they come together, they form water. So this happens naturally in the environment. We call them the products. So this is how you write it. The left side of the arrow is the reactants, the right side are the products. And if you've taken chemistry, this is probably all review, right? So some important chemical reactions we're going to talk about in this class are cellular respiration and photosynthesis. So what are the reactants in this equation for photosynthesis? Okay, and what do we call those in everyday terms? Carbon dioxide and water. Where does carbon dioxide come from? Yeah, we exhale it. It's a product of metabolism. All living things give off carbon dioxide as a product. And then on the right side, what are the products of photosynthesis? What do we get as a result of photosynthesis? Yep, so this is the formula for glucose. So sugar, that's the food, that's the start of the food chain, and oxygen, which we need to breathe, right? Do plants use sugar? Yeah, they need to grow, right? So they make energy, so they undergo photosynthesis, but they also use that energy to grow and develop. Okay, so acids and bases is the next topic, and I think I'm going to save that for when we get back together because that's a whole different topic. So we'll